Hello everyone, can you all hear me? Can you all hear me?
Yes, sir.
Okay, so let us start. So in the last class, we studied till the part. Told you to take some screenshots, right? Did you take those screenshots in the last class? Did you take those screenshots, students? Yes or no? Can I get some responses in the form of voice messages? Yes. Okay, fine. So now we'll be continuing to the next section, right? So please, someone speak up, okay? If I ask, only one of you speak up. I don't have any problem with that. Just speak up when I ask something. Did you see my? Are you able to see my screen? Guys, able to see my screen? Are you guys able to see my screen, students?
Yes, sir.
Okay, fine. So now let us go to the topic analysis of slab decks. Now look, in the last class we discussed an important factor, design coefficient of flexural members, right? So this is the formula for flexural members, and these are the values. Now, if you remember, I told you guys to remember some one formula. So now what we will do is in the analysis of slab bricks. Now look, reinforced concrete slab bricks are used for small span culverts that are generally spanning in one direction, and hence the moments due to dead and live loads are critical in the longitudinal direction, that is the direction of moving loads. Bridge deck slabs simply supported on other sides have been designed for IRC loads specified in class AA or A depending upon the importance of classification of the bridge. In case of reinforced concrete T-beam bridge, the deck slab is supported along the longitudinal and lateral directions by main and post girders. Hence, the slabs in such cases have to be analyzed for movements developed in the longitudinal and lateral directions. So now look, that the load patterns are different for different kind of loadings, right? So we have IRC class A, class AA, class B. Okay. So on the basis of these load patterns, we have different design elements. How a bridge structure will be designed or something like that, right? Now, now look, there, if you can see here, suppose the bridge decks slabs that are simply supported on one side have to be designed for IRC loads specified as class AA or A. Okay. Now, as per those classifications, IRC class AA or class A, The bridge deck slabs that are simply supported on either side, those have to design in that way. Fine. Now, if you can see, in case of RCC concrete T-beam bridge and slab bridges, the deck slab is supported along the longitudinal and lateral directions by main and cross girders. So, in case of simply supported, we have to design the bridges depending upon the different IRC loads like class AA or class. On the other hand, if it is a T-beam bridge, then we have to find out the moments that are developed in longitudinal and lateral directions. Okay. Now, with different support conditions, we have to do the slab analysis, right? So, here are the analysis of slabs with different support conditions. Okay. Number one, solid slabs that are spanning in one direction. Now, for solid slabs spanning in one direction, can you tell me what is solid slab spanning in one direction? Can you tell me what is one-way slab? This is done one-way slab, right? Can you tell me? Anyone please volunteer and say me what is slab spanning in one direction? Can anyone say me what is slab spanning in one direction? Can anyone say me? I don't have any response from anyone. So why don't you say me? Why don't you say me that what is one-way slab and what is two-way slab? What is slab spanning in one direction and what is slab spanning in two directions? Just tell me about it. No idea. No idea.
One-way slab
Hmm.
has two supports and
No, 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 no,
two-way slab has
no, no,
four support.
no. It is dependent on the L by B ratio. Okay. In one way slab, the L by B ratio is greater than 2. Fine. Is it clear? And in two way slab, it is less than 2. Is it clear now? So now, look, for a single concentrated load in case of slab spanning in one direction, the dead moments are directly computed by SOS. Slab to be simply supported within the bearings. So, so this is what is called solid slab only. For now, look, the live loads of vehicles are considered to be transferred through wheels are considered as concentrated loads that are spread over compact area of tires with the brake slab. The bending moment per unit width of the slab developed by concentrated loads on solid slabs may be calculated by assuming the width of slab considered as effective in resisting the bending moment due to concentrated loads. Now, in case of precast, can you tell me what is precast slab? Do you know what is precast slab? Look, for precast slab, the precast means what? It has been made in some other places and it is brought to the site. Okay, that is known as precast slab. Now, for single concentrated load, the effective width may be calculated by this equation. C equal to Kx 1 minus x by L plus Bw. Now, look, BC is what? The effective width of slab with which the load X. L is the effective span. X is the center of gravity from load from nearer support. Bw is the breadth. Hmm. And A is the constant depending upon the ratio D by L. Okay. Now, the value of K for different ratios of D by L is compiled in table 3.5. Now, these are the values of constant K. Now, just take a screenshot of this because these all are important for your exam. Have you taken the screenshot? Tell me.
Yes, sir.
Okay, good. So after this, we discuss two or more concentrated loads in the line in the direction of the span. Now, these are the different cases. So for the first cases, this is K 1 minus x by L plus BW. Okay. Now for the second case, is two or more concentrated loads in the line in the direction of the span. When two or more concentrated loads are positioned in the line in the direction of the span, then the bending moment per unit width of the slab shall be calculated separately. Okay, so separately for each load according to its appropriate effective width of slab as specified under single concept. Okay, that means what? The bending moment per unit width of the slab will be calculated separately for each load. That means bending moment calculation will be different for different types of loads. Huh. Now, coming to the next one. This is the another case, two or more concentrated loads that are not in line in the direction of the span. Okay. Now we'll go to the next one. This is called solid cantilever slab. Okay, I don't have any problem if you interrupt me in between. Okay, and just tell me during if my voice is cracking or something like that. Someone just now told me my voice is cracking and it's clear at times. Is it cracking still? Can anyone please respond? Is my voice still cracking? Can anyone please respond? Is my voice still cracking? Please speak up. Is it cracking? Hello? Is it not audible to all of you? हेलो.
Yes,
क्या सुनाई नहीं दे रहा है तुम लोग को? दे रहा है? हाँ हाँ.
yes,
क्या बोल
আহি
रहा
আছে
है?
sir.
I'm not hearing anyone. Can
Sir,
anyone?
শুনা পাই আছো.
Okay, fine. You are hearing now. Those who have written
Yes,
yes, they are hearing now. Fine, fine.
yes, sir.
Okay, okay. So if it is like cracking sometimes, maybe it might be network issue on your part also, on your place also. Try to move to a different place. And if it is cracking for all of you, then it's my issue. So tell me about it. Okay? Just unmute yourself and then you can tell. Okay? I don't have any problem. Now, for a solid cantilever slab, the effective width of dispersion in the direction parallel to the support edge for a simple concentrated load is this one. C equal to 1.2x plus BW. Now, if you see here, you can see here, this is BE, okay? This is BE. So BE is effective what? Width, okay? So this is BE. For your convenience, better you buy this book, then it will be comfortable for you to also to study. Okay? Better buy this book. I might find the link, then I'll send it to you. Now, if you can see here, this is for the solid cantilever slab. Now, this thing, let me explain. Now, this is what? Effective width of dispersion, right? That means what? Suppose this is the width of the load part. Now, if you see, these are the layers. So now, if you see here, this way, so if you can see here, okay, so this is the load and it will be dispersed like this. Now this width, now suppose this is the part where, hello, can you all hear me? Can you all hear
Yes,
me?
sir. Yes,
Okay,
sir.
okay, fine, thank you. So now this is the part where the vehicle will be going, right? This is the part where vehicle will be going. Now this, look, now this is the part of the bottom of the road, now. So if this vehicle is moving here like this, then the load will be dispersed here in this way. And this is denoted by what? B and E. Okay. So now this is the BE. That means BE is the effective width. Now BE is what? Different for different values. Now for solid cantilever slabs, this is the value of BE. Okay. So now how will you find out this one? This is how it is being found out. Okay. So these are the different criteria. Now if you can see, the effective weight, that is the BE, it should be what? It should be limited to 1/3 of the length of the cantilever slab, that is measured in parallel to the support. That means the slab which is present. Now, if you measure, why my voice always fails?
Tell me if it is cracking now also, okay? Now for a solid cantilever slab, if you can see it, the effective width should be limited to 1/3 of the length of the cantilever slab and which is measured parallel to the support. Okay. Now when the concentrated load is placed near to one end of the extreme ends, the effective width should not exceed the above value, nor half the above value plus the distance of concentrated load from the near extreme ends. These are conditions which are okay, but the main thing is that you have to remember BE equal to 1.2x plus BW. This is the formula that you have to remember. Okay. So now these are what it denotes actually for solid cantilever slab. Okay. Now those who are like willing to note it down, you can note it down, or you may get the video in the link also. No problem with that. But if you want to note it down, you can note it down also. So is my voice still cracking now? Someone please pick up and say
No, sir, it's clear.
it's clear now, right? Okay.
Yes,
If
sir.
it is cracking, then please interrupt me and tell me, okay? Then I'll check my network connections. Fine. Now, if you see here, now dispersion of loads along span. First of all, it was what? Solid cantilever slab, right? Then dispersion of loads along the span. Now, along the span of the bridge, the loads will be dispersed in this relation V equal to x plus 2 d by h. So V is the what? Effective length of dispersion along the span. Now look, this was what? In the direction of moving of the vehicle. And now this one is what? Along the span. Okay. So now if it is along the span, then we have this reaction, the relation. V equal to x plus 2 d by h. Fine. So these are the relations. The most important is B equal to 1.2x plus BW. This is the most important. Now if you go down, dispersion of loads that is spanning in two directions. Now dispersion of loads spanning in two directions, these will be, computed by using design curves that are developed by Pitotz and Westergaard's. Okay. Now this Pitotz curve and Westergaard's curves, these are the very important curves. So these curves, what I'll do is I'll share in the group. Okay. I have this from the book also, but then I'll just share it with you. Huh? So if you can take a printout, it will be better for you people for solving the numericals. Okay, so these are the Pitot's curve. The dispersion of slabs for slabs spanning in two directions. What is being done is we'll have Pitot's and Westergaard's. Okay. So now let us do one thing.